Hello students, I welcome all of you in this lecture. In this lecture, we will move forward towards the new section from our unit rings and ideals. So we are going to discuss here local rings and equivalent conditions of local rings. So let me first of all start with it. So let me write it. Local rings and equivalent conditions. Equivalent conditions. Okay. So first of all, let me define local rings. A local ring, a local ring is a ring with exactly one maximal ideal with exactly one maximal ideal. Okay, so the maximal ideal, that unique maximal ideal, is denoted by mr. The maximal ideal is denoted by mr. Okay, and that's why it forms a structure. What can be that structure? So definitely we have ring. Okay, then we have its unique maximal ideal, and then we have field k. Okay, what is this field k? So definitely if mr is the maximal ideal, then quotient ring will be filled, and that fraction field is called as k. Okay, so this is one structure that we can have from this particular idea. Okay, so let me just erase it. Okay, that is local ring is a structure. So local ring is a structure R, then mr comma k, where k is nothing but its residue field of that maximal ideal, where k is equal to r upon mr. Okay, is residue field. Fine. Okay, fine. Now let's directly jump to the equivalent conditions of local ring. So we have a lemma here. Lemma: let r be a ring. Let r be a ring. Then the following are equivalent. Then the following are equivalent. So what are the conditions? Let me write them one by one. First condition: R is a local ring. Second condition: spec of R, that is spectrum of R, has exactly one closed point. Has exactly one closed point. Then we have R has unique maximal ideal. R has unique maximal ideal m, and every element of every element of R upon m is a unit. And last condition: R is not the zero ring. R is not the zero ring, and for every x belongs to R, and for every x belongs to R, either x or 1 minus x is invertible, or both can be invertible, is invertible, or both. So these are the equivalent conditions of local ring. So R is a local ring, spec of R, spectrum of R has exactly one point. What is spectrum of R? That is nothing but set of all prime ideals. I will write it later. R has unique maximal ideal M, and every element of residue field R upon M is a unit, and R is not the zero ring. Okay, and for every x belongs to R, either x is unit invertible or 1 minus x is invertible. That 1 minus x is unit. Okay, so let's now prove these conditions one by one. So let's move to the proof. So first of all, we will see 1 implies 2. Okay, so suppose R is a local ring. Suppose R is a local ring. Local ring. But before this, let me just shortly define what is spectrum of A. So spectrum of A is nothing but set of all prime ideals. So let me just erase this, and let me first of all write down spectrum of A, so that we can have that idea in discussion. So spectrum of ring, okay, or spectrum of R is nothing but the set of all prime ideals of R. Set of all prime ideals of R. It is usually called as prime spectrum. Okay, set of all prime ideals of R, that is your spec of R. Okay, no doubt. Now let's move to the proof. So I was talking about 1 implies 2. Suppose R is a local ring. Suppose R is a local ring. Okay, then by definition of a local ring, then clearly R has unique maximal ideal. Then clearly R has unique maximal ideal. Okay, and hence unique prime ideal, and hence unique prime ideal. Unique prime ideal. Okay, no doubt. So what does this means? This means that the spectrum of R has that is set of all prime ideals has exactly 1 point. Okay, it has exactly 1 point, right? Yeah. So hence unique prime ideal which is closed, right? Which is closed, because I want to say that suppose M is the maximal ideal, means R is the local ring, so it has unique maximal ideal, say M. Okay, then every maximal ideal is prime ideal, so this is prime ideal, right? This is prime ideal. And if you find out its closure, suppose let's call it as P, and if you find out its closure, okay, then this is the set of all prime ideals containing P. Okay, but there is only one prime ideal which contains P, because M is maximal, right? So it is not contained in any other ideal, so its closure is singleton P itself, so it is closed, right? So that means if R is local ring, then spec of A, spectrum of R, has exactly one closed point, and that is the maximal ideal, which is also a prime ideal, right? So let me just erase these points. Karana unique prime ideal which is closed, so it is very trivial, right? No doubt. Because let me write here, because that unique maximal ideal, that unique maximal ideal is the only prime ideal, is the only prime ideal which is closed. Okay, which is closed. So that's why if R is local ring, then there is exactly one close point. So spectrum of R has exactly one closed point. Okay, now let's have 2 implies 1. Okay, suppose spectrum of R has exactly one close point. one closed point. Okay, then we have to prove that R is a local ring. Okay, spectrum of R is exactly one closed point, so we need to prove that R is a local ring. Say P. Let me write say P. Let M and M dash be two maximal ideals of R. Actually, we need to prove that there is exactly one maximal ideal. So let me assume that there are two maximal ideals. Okay, then both of these ideals are prime because every maximal ideal is prime. So then M and M dash are prime ideals. Right? These are also prime ideals. Okay, now if you find the closures of this, okay, also closure of M is equal to M. So M is, because M is the only prime ideal which contains itself, and closure of M dash is equal to single M dash, right, is equal to single M dash, because it is also, you can see that it is the only maximal ideal which contains itself, which is the only prime ideal which contains itself, right? So that's why closure, दोघांचा closure same येतोय. So what this implies, both are closed points, right? So this implies M and M dash are closed points of spectrum of R, closed points of spectrum of R, which is not possible because spectrum of R has exactly one closed point. But this is not possible, right? But this is not possible. But this is not possible because as per the assumption, it has exactly one closed point. So R has unique maximal ideal. So R has unique maximal ideal. This implies R is a local ring. This implies R is the local ring. Okay, no doubt. Now let's go to the next part of this. Now I need to prove that 1 implies 3. So I will prove the equivalence of 1 and 3. 1 implies 3. So suppose R is a local ring. Suppose R is the local ring. Okay. First of all, let's have a look at what we need to prove. We need to prove that R has unique maximal ideal and every element of R upon M is unit. Right? That is what we need to prove. Now, since R is a local ring, definitely it has unique maximal ideal. Okay. Clearly R has unique maximal ideal. Okay. Say M. Now we need to prove that every element of R upon M is unit. Okay. So let me consider an element. Let X belongs to R upon M. Right. Okay. If X is not unit, if X is not unit, then what will happen? Then definitely it is contained in some maximal ideal, right? Because maximal ideal मध्ये units असू शकत नाहीत, बरोबर? कारण maximal ideal मधला element unit असेल तर that maximal ideal is equal to ring, which is not true, right? So if X is not unit, then there is another maximal ideal, then there is another maximal ideal then there is another maximal ideal. Just a second. It is R minus M. Okay, so if X is not unit, then there is another maximal ideal M dash such that X belongs to M dash. राईट, कारण एक्स हा एम मध्ये नाही आहे, कारण तुम्ही आर मधून एम काढून टाकलाय. सो एक्स हा एम मध्ये असू शकत नाही. सो देर एक्झिस्ट अनदर मॅक्सिमल आयडियल सच दॅट एक्स बिलॉंग्स टू एम डॅश. राईट. ओके, नाव व्हॉट हॅपन्स, नाव इफ एक्स बिलॉंग्स टू एम डॅश, okay, then it is not possible. Why this is not possible? Because you can easily find out. If this is so, then there are two maximal ideals in ring R, but R is local ring, so it has unique maximal ideal. So if X is not unique, then there is another maximal ideal M dash such that X belongs to M dash. That is, R has two maximal ideals. R has two maximal ideals, M and M dash, right? This is not possible because R is local ring that we have assumed. So this is not possible. Okay, so whatever we have assumed, that must be wrong. So X is not unit, what was our assumption. So X must be unit, so X is unit, right? So this proves 1 implies 3. Now let's jump to the 3 implies 1. Suppose R has a maximal ideal M. Suppose R has a maximal ideal M, okay, and every element of R minus M is a unit. Let's assume this. Now we need to prove that R is a local ring, right? So we must prove that R has unique maximal ideal. Okay, no problem. Now let us assume that there are two maximal ideals in R. Okay, suppose, or let us say that, assume that M and M dash are two maximal ideals of R. Are two maximal ideals of R. Okay, no problem. Choose X belongs to M dash such that X does not belongs to M, right? X belongs to M dash such that X does not belongs to M. Okay, so what happens? X belongs to M dash. So M dash is a maximal ideal. So X belongs to M dash, but X does not belongs to M. M पर मॅक्सिमल आयडियल आहे आणि X हा M मध्ये नाहीये. जर X हा M मध्ये नाहीये याचा अर्थ X हा युनिट असू शकत नाही, राईट? का? कारण जर इट्स व्हेरी क्लिअर की द आयडिया इज व्हेरी सिम्पल, कारण X हा M डॅश मध्ये आहे, मॅक्सिमल आयडियल मध्ये आहे तो, आणि मॅक्सिमल आयडियल मधले एलिमेंट्स युनिट असू शकत नाहीत, कारण जर युनिट असेल तर दॅट इज इक्वल टू रिंग, ॲज आय टोल्ड यू प्रिव्हियसली. सो X बिलॉंग्स टू M डॅश आहे. सो व्हॉट दिस इम्प्लाइज X इज नॉट अ युनिट. X कॅनॉट बी अ युनिट. X इज नॉट अ युनिट. बट आपलं ॲझम्पशन काय आहे? एव्हरी एलिमेंट बिलॉंग्स टू आर मायनस एम इज अ युनिट. म्हणजे आर मधून एम काढून टाकला तर बाकी सगळे एलिमेंट्स युनिट असतात. बट आपण एक एलिमेंट फाइंड केला एक्स, जो की एम मध्ये नाही आहे. ओके, पण तो युनिट पण नाही आहे, राईट? विच इज अ कॉन्ट्रडिक्शन, टू अवर ॲझम्पशन, विच इज नॉट पॉसिबल. So this clearly means that there must be single maximal ideal, right? So thus R must have a single maximal ideal. So this implies R is a local ring. Okay, no doubt. Now let's go on to prove the equivalence of 1 and 4. So I need to prove that 1 implies 4 and 4 implies 1. So let me just prove that 1 implies 4. So first of all, have a look. What is the statement 1 and what is the statement 4? So statement 1 reads that R is a local ring, and statement 4 reads that R ignores the zero ring and every X belongs to R. Either X is unit or 1 minus X is unit, or both. Okay, so let's first of all assume that suppose R is a local ring. Suppose R is a local ring, right? Let X belongs to R be an element, Okay, now since R is a local ring, it has unique maximal ideal, right? So since R is a local ring, comma, it has a unique maximal ideal, say M. Okay, so now there are two cases. Okay, what happens if X belongs to M and if X does not belongs to M, right? So this is your ring R, right? This is your unique maximal ideal M, and this is your point X, right? Now this point is either in M or this point is not in M. That are the two cases which can are possible, right? Okay, so no problem, let me just assume the first case. Okay, if X belongs to M, then what happens if X belongs to M? Okay, uh, if X belongs to M, then X belongs to Jacobson radical. Why it belongs to Jacobson radical? Because we know that Jacobson radical is the intersection of all maximal ideals, right? रिंग मध्ये एकच मॅक्सिमल आयडियल आहे तो म्हणजे यम. सो जॉकॉब्सन रॅडिकल या मॅक्सिमल आयडियलचं इंटरसेक्शन म्हणजे यमच येणार. ओके, कारण सिंगल मॅक्सिमल आयडियल आहे आपल्याकडे, त्याच्यामुळे जॉकॉब्सन रॅडिकल इक्वल टू यम येईल. बरोबर आहे. सो एक्स जर यम मध्ये असेल तर डेफिनेटली एक्स बिलॉंग्स टू जॉकॉब्सन रॅडिकल असणार आहे, राईट? अँड वी हॅव सीन वन रिझल्ट बेस्ड ऑन द जॉकॉब्सन रॅडिकल. सो लेट मी जस्ट jump to that result. Okay, so we can easily use that result in our current discussion. Okay, so result is that if X belongs to Jacobson radical, if and only if 1 minus X into Y is unit for every Y in A, म्हणजे रिंग मधल्या प्रत्येक Y साठी 1 minus XY unit असतो, right? So if X belongs to M, then X belongs to Jacobson radical. This implies 1 minus XY is unit in R for every Y belongs to R. Okay, so if we take Y equal to 1, then what happens? Okay, if we take Y equal to 1, then 1 minus X is unit. 1 minus X is unit in R. That's very simple. So this was the first case. Assume that if X does not belongs to M. Okay, definitely if X does not belongs to M, then it must be unit. कारण X जर M मध्ये असता, okay, then it cannot be unit कारण that may be equal to ring, right? So if X does not belongs to M, then definitely X is unit. Then X is unit. So what we proved, जर X M मध्ये असेल तर 1 minus X unit असतो, X M मध्ये नसेल तर X स्वतः unit असतो. So in either case, so either 1 minus X or X is unit in R, right? ह्या दोघांपैकी एक कोणतरी unit आहे. So that is what our statement was. And let's now prove the final, that is 4 implies 1. So suppose R is not a zero ring. Okay, suppose R is not a zero ring. Okay, and also assume that, suppose R is not a zero ring, assume that for every X belongs to R, either X or 1 minus X is unit or both. हे अजून करा. क्लेम आपला असेल R is a local ring. Claim R is a local ring, right? Okay, आता R local ring दाखवण्यासाठी we have to prove that it has exactly one maximal ideal. So let M and M dash be two maximal ideals of R. Let M and M dash be two maximal ideals of R, right? Okay, then definitely we can select X such that X belongs to M. Okay, but X does not belongs to M dash. Okay, choose X belongs to M such that X does not belongs to M dash. कारण दोन मॅक्सिमल आयडियल आहेत, तुम्ही डेफिनेटली एक एलिमेंट असं फाइंड करू शकता की जो M मध्ये आहे पण तो M dash मध्ये नाहीये. ओके, आता एक्स जर यम मध्ये आहे, मॅक्सिमल आयडियल यम मध्ये आहे, म्हणजे डेफिनेटली तो युनिट नाही आहे. ओके, सो एक्स इज नॉट युनिट. दिस इम्प्लाइज एक्स इज नॉट युनिट, कारण तो मॅक्सिमल आयडियल यम मध्ये आहे, सो तो युनिट असू शकत नाही. राईट. सो आपल्याकडे ऑलरेडी एक मॅक्सिमल आयडियल आहे यम डॅश, आणि हा एक युनिट नाही आहे. सो व्हॉट कॅन हॅपन देन, मॅक्सिमल आयडियल यम डॅश प्लस या एक्स पासून जनरेट झालेला आयडियल जर ॲडिशन केली तर दॅट मस्ट बी इक्वल टू रिंग. का? कारण यम डॅश मॅक्सिमल आहे, यम डॅश मॅक्सिमल आहे, सो त्याच्यामध्ये जर तुम्ही हा आयडियल ॲड केला, ओके, सर नवीन एक आयडियल तयार होतं, ॲडिशन ऑफ आयडियल्स. सो एम डॅश हा ऑलरेडी तुमचा आयडियल आहे, प्लस तुम्ही अजून एक त्याच्यामध्ये आयडियल तयार केला, ॲड केला, तर दॅट विल फॉर्म अ न्यू आयडियल. ओके, अँड दॅट ॲडिशन इज इक्वल टू रिंग. Okay, definitely this is equal to ring because m dash is maximal. So what happens? So that is equal to ideal generated by 1. Okay, so this implies 1 belongs to m dash plus ideal generated by x. Okay, so 1 belongs to m dash plus ideal generated by x, or we may say that 1 minus x belongs to m dash. 1 minus x belongs to m dash. Okay, and if 1 minus x belongs to m dash, then definitely what happens? Because it's very simple, you can write 1 as a addition of element of m dash plus element of this ideal generated by x. Okay, so 1 minus x belongs to m dash. So what does this gives? This gives 1 minus x is not unit because it belongs to m dash, so 1 minus x is not unit. Okay, and if 1 minus x is not unit, then this is contradiction because x is also not unit, 1 minus x is also not unit, which is not possible, right? This is contradiction to our assumption. This is contradiction. Why this is contradiction? Because neither x nor 1 minus x is unit. ओके, सो कारण आणि आपण ॲझ्युम केले की दोघांपैकी एक कोणतरी युनिट असायलाच पाहिजे, बट नायदर एक्स नॉर 1 minus x is unit. So what happens? So this is contradiction. Thus R must be a local. Thus R has exactly one maximal ideal, right? This implies R is a local ring. So this proves the equivalence of all these statements, right? Now basically equivalence means that we can prove any statement from any given statement, right? So now suppose I want to prove that 2 implies 3. Basically we haven't proved that 2 implies 3, but suppose I want to prove that 2 implies 3, then how can I go with it? Okay, so I can easily go with this, like say, because this equivalence has been established, if I want to prove that 2 implies 3, then I can go in this way. First of all, I will prove that 2 implies 1, and then I will prove that 1 implies 3. So this transitively will mean that 2 implies 3. Suppose I want to prove that 3 implies 4. Then first of all, I will prove that 3 implies 1, and then I will prove that 1 implies 4. So 3 implies 4. So basically, we can see that all these statements are equivalent to each other. So this establishes the equivalence of all these statements. So if R is local ring, then we can have 4 alternative definitions for this. If R is local ring, then it has unique maximal ideal. If R is local ring, then the spectrum of R has exactly one close point. R is local ring if and only if R has maximal ideal M, and every element of R minus M is unit. And if R is local ring, then for every x belongs to R, either x or 1 minus x is unit. So because of this, the equivalence statements, we can have 4 alternative statements for the definition of local ring. Okay, so this is all about the local rings and equivalent conditions of local rings. Okay, so you can use any of these statement as a definition for local ring. That means if you want to prove that some ring is local, then either you can go with the idea that it has unique maximal ideal, or you can go with the idea that for every x, either x or 1 minus x is unit. Okay, so in either case you can prove that it is a local ring, or you may also prove that spectrum of that ring has exactly one close point. Okay, or you may prove that R has maximal ideal M, and every element of R upon M is unit. That you also prove. Okay, let me just release this word unique. R has maximal ideal M, and every element of R upon M is unit. Okay, so in this manner you can use these ideas for to establish that some ring is local. Okay, so this is all about local ring. With this I stop here in this lecture. Thank you.